Hello students, in earlier video you have gone through some basics about NEET in connection with interference, and in that we discussed about two types of interference, constructive and destructive, conditions for the respective. Continuing ahead, in the present video, we shall discuss about few more important things from interference and exclusively from the perspective of NEET examination. You all know in interference you got a modification in the intensity of light depending upon how the two or more than two waves at a particular place are superposing. Accordingly, at a point on the screen you get either maximum intensity or minimum intensity, and that exclusively gets decided by phase in superposing waves or path difference between superposing waves. To visualize this, as I have before also, scientist Young has made up a simple setup to visualize interference, demonstrate interference. You have studied as Young's double slit experiment. So by taking the help of this experiment, we have certain important points or formulas that we are going to cover in the today's class. You know, from Young's double slit experiment, you could see that alternate there are bright and dark region in the interference pattern, and you know these alternate bright and dark regions are called as fringes. So let me first remind you about these fringes in the interference pattern. Fringe wave we define as separation between conjugative bright or conjugative dark fringes, or separation between conjugative dark bands and bright bands. We call it as a fringe wave. Remember that I used the word dark bands and bright bands. It's not separation between conjugative dark bands and bright bands. Rather, I should say separation between conjugative bright or conjugative dark we call as a fringe wave. These are all basic things and simple things you have studied. Straightforward. Let me go ahead with the Young's double slits setup, and from there I need to remind you certain basic formulas, fundamental formulas, which we should be ready with while appearing NEET examination. In the setup, you have got double slit to the plane, which is provided with the two holes, openings. You call them as the slits. Slit S1 called slit S2. And over here we have arranged what I have got this as a screen. This you refer as the center of screen. And that's the reference point for all measurements. Measurement of all distances. Center of screen. Now I have a point of my interest on the screen So this is a point P. At this point P, not only at P, everywhere, I will have the waves arriving from source S1, source S2. Now whether this P is going to be bright or dark, that gets decided by path difference or phase difference, you can say. And what you do, well, you derive the expression. You have worked out path difference between these two superposing waves. So I mean, path travelled by this wave plus path travelled by this wave, we have worked out. By referring to the tree, you have worked out that. So path difference here is S2 minus S1P. And by having this small d, separation between two slates, this separation as capital D, distance of screen from slate, and this distance as x. I mean the distance our study from center of screen. So by referring to this figure, you have got this value first, and you get that as path difference 2p minus S1p, or that xd divided by capital D. Important one. For the competitive examination, I will have to have reference of this while solving some questions. Path difference between two opposing waves I have got given by this expression. Now it is the value of this path difference which will decide whether P is going to be bright or dark. If this path difference, as per the condition that we studied, if this path difference is 0, lambda, 2 lambda, 3 lambda, and so on, an integral multiple of lambda, you will have point P as a bright. If the difference is lambda by 2, 3 lambda by 2, 5 lambda by 2, I mean odd integral multiple of lambda by 2, you will have point, dark region. Anyhow, now my next important over here, I may have to know distance of particular bright band or dark band on the screen. Say at P, I have got some third dark band, so that X will give me the position band. Say at P, I have got some nth bright band, so this distance X will give me the position of nth bright band. So I should know which will guide me to know distance of either bright band or dark band from center of screen. And by following certain simple steps, the formula as I write here XNB, N for number of that fringe, nth fringe, nth band, and B for bright. So at P for nth bright band, then the distance of that nth bright band I have worked out, and I get that as n lambda d by d. Important one. So what is this? Location of nth bright band of the screen with respect to, of course, center of screen. Similarly, if I want to know where is the nth dark band on the screen, and what is the location of nth dark band, for that again this is my basic. Having this, I will substitute as a 2n minus 1 lambda by 2, and if I rearrange it, what I get is X and D. Again D I am using for dark, and that I get as 2n minus lambda by 2 d by d. So, location of nth dark band on the screen. So important thing. In this equation, I would note position of nth bride, position of nth dark. Now once I am ready with this, position of nth bride band, as per the basic definition, you know, separation between conjugative bright or conjugative dark will give us a fringe width. On the screen, I am using a monochromatic light. I get the pattern of this kind, like this has a bright band, particular color, then I will have a dark, again a bright, then I will have dark, again a bright. So this kind of fringes I am getting. So our interest is to know width of those fringes. Whether bright or dark. I would like to know what is the width of bright fringe and dark fringe. For that, by getting a separation conjugate dark, you will get a width of bright. By getting a separation between conjugative bright, width of dark. If you do that, you get width of in the interference pattern given by expression. You have derived that. What I need to remember here is this expression. This is the expression for fringe width. I can see clearly from that expression. Fringe width depends on some basic parameter. I have got light used as a monochromatic light, you can see. More the wavelength of that monochromatic light. So I can mention that fringe width is directly proportional to wavelength. Some simple type of comparative type of questions I may have in competitive exam. Like if a source of wavelength lambda 1 is replaced by a source of wavelength lambda 2, how that will affect to the fringe width? Straight away I can follow this relation. I can refer to this relation. Similarly, I can see that fringe width depends directly on separation between plane of the screen and plane of the slit. More is that separation, more is fringe width. Whereas I can see that fringe width depends inversely on the separation. Slit. At more separation, I can see that fringe width is going to be less. If I have slit separation is small, I will have fringe width more. So, fringe width gets decided by separation of two slits. So, these are the important things to be remembered while dealing with questions in the competitive examination. Once I am done with this, now the next important thing I would like to discuss over here. So whatever these parameters I have discussed, these I call as a linear parameters. So I mean, this I will call as the position of nth bright band. I mean linear position. This I will say position of nth dark band. Linear call of nth dark band. This I have got width of the fringe width I have, linear fringe width I see. But in competitive examination, I may deal with angular parameters also. So what I mean by that, just I'll bring to your notice. See here, again the same setup I will have. So these are the two slits. This is your screen. Of the screen on the center on the screen, say I have got a point P here, which is either bright or dark based on difference. This distance I have got, let us say, so what that X represent? I would say linear position of the point P. But in competitive examination, I may have to write angular position of that P. So for that, what I mean is that from center of these two slits, I have this line to be drawn. Now this line makes an angle certain theta with my reference line. Reference line you can say. So this angle theta gives me angular position of the point P. Linear position is x, angular position is theta. And if I correlate these two, I can do that by my simple basic knowledge about trigonometry. I can relate this x, d and theta. D is the radius of the arc which I have. X is the arc length. Simple things. So if you relate that, what you get is x equal to L equal to r theta. D into theta I can write. And now with this basic, so at P I have got nth bride band. And that theta will give me the angular position of nth bride band. If at P I have got nth dark band, that theta will give me the position of nth dark band. So by referring this relation, I can write an expression for angular position of nth bride band. X value already I have got it, and that gives me n by d. Similarly, angular position of nth dark, I get it as referring to this 2n minus 1 lambda by 2 into d. It's important thing. This is the expression for angular position of n, right? This is the expression for angular position of nth dark. Same way, say at P, I have got this as a something bride band. Over here, this distance I have called as a fringe veil, linear fringe veil. Now, if I have to talk about this separation, what I mean is here, this one, that is angular separation, angular width of this region you can say, and that angular width I call as angular fringe veil. I get that by simple steps. D theta I call that as a lambda divided by d. What that equation gives me? Angular fringe weight. So this is the expression for angular fringe weight. Now one thing you might have noticed, what is that? From these expressions, if I remove capital D, now left out whatever is there, those are nothing but angular parameters. Important thing. So separately you need not to break your head to remember the expression for angular parameter. So what you need to add to your memory, just eliminate capital D, whatever left out is angular parameter. So this is an important thing to be remembered. Now going ahead, competitive examination, I may have a situation where I have to answer like if the whole setup is placed in some other area other than air. Now what would be the impact of that? Simple thing. Let us see then. What would happen if the whole setup is put into water? Now you can see, without altering any of the parameters, I mean neither small d changed nor capital D changed, the only thing, media through which the light emitted is to propagate, and the media now. And you know, when light travels from one medium to another, its wavelength will change. So that change in wavelength will affect to all the parameters. Due to change in wavelength, I will have change in the position of nth bright band. You can see here. Due to change in wavelength, I will have change in position of nth dark band. Due to change in wavelength, I will have change in the fringe width also. And if I am asked to write now new fringe width, say in water I am writing. What should I write? Wavelength of light in water into d, which is not changing, by small d, which is not changing. What has changed? Only wavelength. Now that change in wavelength, I should think, can it be related, that new wavelength I mean, can it be related with earlier wavelength? Yes, of course. We have got wavelength of light in air and wavelength of light in any another media related by one simple relation. It is mu equal to lambda A by lambda W. So that's it. If I am aware of this for lambda W. And what is the value of lambda W now? Lambda A by mu. I'll substitute over there and I get then fringe width in that new media or water media equal to, for this, that is lambda A by mu into d by d. See what new term has come is a mu, and you can very easily understand that. So what does represent for fringe media when the setup was in air? So I can write then fringe width in water to fringe width in the air divided by refractive index. Very important formula. Whenever a YDS setup is put into any another media, the new fringe width you get given by this relation. So what has come in the denominator is a mu refractive index. A simple thought-provoking question. Will this new fringe width will be less than or greater than earlier? Easy to understand. You know, mu for any media is greater than 1. Minimum it is for vacuum 1. For all other media, absolute refractive index or this refractive index is greater than 1. Then naturally, fringe width for the given setup will be maximum in the air, and for all other remaining media it is going to be less than air, you can say. What this? There are the questions which have been asked repeatedly on this formula. Okay. So going ahead, now few more important things. about parameters which we have got in a YDSC setup. So the situation is like this. The setup again. Center of screen. Now in this setup, instead of using monochromatic light, I am using a source which has two wavelengths like a lambda 1 and lambda 2. With single wavelength, say if it is a red light source, I would have screen alternate red band, dark band, red band, dark band. But now I have got, well, see it is a green color. So I get even the fringes of green color. Green color bright, dark region. Green color bright, dark region. So I mean bright fringes of two different color and at two different location I'll get. Then during such situation, there are chances that bright fringes of those two colors are superposing, are overlapping at certain places. And we will have a question on that overlapping process fringes if you use source of two different wavelengths. So let's learn then some basics about overlapping of fringes. And particularly on this, they ask you in competitive exam. See that overlapping multiple places. Like at one of the place, third of one and fourth of another, third band and fourth bright band of another are overlapping. But that may not be the only place. I may have again 10th of one color and 15th of another color overlapping. I mean, overlapping may happen multiple times. But generally in the competitive exam they'll ask you least distance from center of screen where the two fringes are overlapping, two bright fringes are overlapping, and I'm interested about to get that least distance. Say for example, I have one place on the screen, point P. What I could see is that I have bright, nth bright of wavelength lambda 1. At the same place, I have got bright of wavelength lambda 2. Understand? So nth of lambda 1 and mth of lambda 2 are overlapping. This distance I would write NB half wavelength lambda 1. This distance I would write XMB half lambda 2. And when I mention that they are overlapping, you simply mean that those distances are same. That's what I write here. So XNB of lambda 1, this is just to discriminate of which wavelength I am writing, equal to XMB of lambda 2. And you know how to get position of any bright band in the pattern. This I will get as n lambda 1 d by this I will get as m lambda d by d. This is going to get cancelled. And what I have got is n divided by m equal to lambda 2 by lambda 1. So whenever I happen to deal with a question of overlapping of the fringes, delay, just I recall this equation. So what that equation is for? It is the ratio of fringe number of wavelength lambda 1 and lambda 2